Record. Go here. Okay, try it now. Yes. Good, good. All right. So our next speaker is Francois Portier. So he's an associate professor at NSAI. And so his research interests are Monte Carlo methods, stochastic statistical learning, and semi-parametric statistics. So, welcoming you, and go ahead. The floor is yours.
Well, thanks a lot for the invitation and the organization. So I'm Francois Portier, I'm from Bretagne, and this is joint work with Rémi Leluc. He was my PhD student when I was in Paris before. So today I'm going to talk about stochastic gradient descent, and what I want to promote is the use of coordinate sampling. So it's really basic. So instead of moving according to the full gradient, we are going to select some coordinate. So at each step, we are going to select some coordinate, and we are going to move only along those coordinates. All right. So the algorithm we are going to define following this idea is called Musketeer, and it's going to be, so the outline is going to be as follows. So first, an introduction where the use of coordinate sampling is going to be presented in the framework of stochastic gradient descent. Then I will introduce my algorithm, Musketeer, then numerical experiment, and I will end with a theoretical result. All right, so here is the background for this talk. So we wish to optimize that function. So we want to reach a minimum of it. And this function is particular. It's an expectation. So this is the field of stochastic optimization. The main issue is that we don't, it's hard to compute the gradient. So if you want to run gradient descent, it's too difficult because it's hard to compute this gradient. So let's look at this first example. This is the running example for the talk. So here you have, so it's the empirical risk minimization example where you wish to optimize this function. So this function is an expectation with respect to a discrete measure, which is the empirical measure with respect to the sample that you observe. And if you look at its gradient, then you can see that it requires an evaluation, which is far too much, especially at the start of the algorithm, where you don't want to lose too much time in computing precise stuff. So another example, so here you can compute it, it's just expensive. Here another example is in adaptive sampling, where you are looking at some divergence between two probability, between two densities, for instance, Q star and Q theta, and you wish to optimize with respect to theta. Here, this expectation has no reason to be accessible, so you don't know it. And so you need to use some approximation of the gradient here. All right, so let's move on. What people are doing is to, introduce noisy gradients. So I'm going to show how you can compute that kind of thing. So here, a noisy gradient is the gradient plus a noise, and you can call it every time you want, okay, in the algorithm. But you're going to have a noise at each step, and the goal is to show that these noisy steps can be controlled in some way, and you still have convergence. So in the example of empirical risk minimization, the picture that I want to share with you is here you have the index, all right? And for each index, you have a gradient. So since this function writes as an empirical distribution, so it's a uniform distribution over the index, what you do at each step of the stochastic gradient algorithm, you're going to select at random an index, let's say it's J, according to a uniform distribution over the index. So this is relevant because we are going to introduce an additional sampling step in this algorithm. All right. So using this kind of gradients that are sampled according to the index set, we can define this stochastic gradient descent algorithm. And another refined version of it is when you include a conditioning step, you multiply the stochastic gradient direction by some matrix. All right, so this has been initially defined in order to reach some optimality in the variance. Here, this is not the target of the talk. Okay, we don't want to reach any variance optimality because we want to face a very large scale problem in which obtaining this optimal variance is not really our main goal. All right, first of all, we want to have an algorithm which is kind of efficient and which is good at the first early stage. All right, so here is the framework that we want to that we are going to use. So as I said, you are going to pick at random a zeta. All right, this zeta variable, as soon as k is different from this zeta, then you don't move. Your iterate will stay where it is. Otherwise, when k equals zeta, then you move according to the gradient intensity. Okay, so here the sign is important. All right, of course. So the goal using this idea is to use some benefits related to the computing cost, of course. Also, one thing that is interesting is that you can use any gradient you want, any estimate of gradient, and this is going to be important. All right, because we are going to use zero order gradient in the end. It's important to be aware that now you have two sources of randomness, one related to the gradient generation and one other related to the sampling of the coordinate. These two, yes?
Quick question, but you still have to compute the gradient over the entire data set?
No, not at all. That's the point. You're going to compute only one. So in the algorithm, you're going to first draw the variable zeta so that you know which coordinates you need in order to move.
Okay. But I'm confused. I mean, like, how's this different from having mini batch one? Like
mini batch.
Like mini batch size one. Like, I mean,
the mini batch size can be one or can be different.
Was what my question was about. This also relates to the mini batch size, but I think I got you now.
Okay, so in the picture that I started before, so
right,
that's a good question to move on. In the picture that I was showing before. So here we have something according to the uniform distribution. What we are going to do is now so here is the dimension. We are going at each stage to select one of those. So here is the zeta. It's going to be sampled according to a distribution that is going to be called T. All right. So here is the framework, and what we want to do is to develop an algorithm called Musketeer that can use some special structure in the data to take advantage of this structure in order to have a better convergence than before. And plus, what we want to achieve, so this is the practical side of our work, and what we want to guarantee is the convergence of such algorithm. Okay, so here is related work that we found relevant. So in fact, the use of this coordinate sampling has been promoted before, of course, and in fact in the coordinate descent framework. Here are some works that are dealing with procedure that consider the evaluation of f and gradient of f. There is no stochastic, all right, related to that. They believe, in their example, they have access to the true f and the true gradient. So this is not really relevant to us, but still some ideas are inside that. The fact that in this framework, it has been shown to be relevant to have a sequence of distribution. So the distribution for sampling the coordinate, the D distribution. So this sequence is going to be indexed by t, and it's going to evolve through time in order to reach some kind of optimal strategy for sampling the coordinates. All right, so it has been shown that you can have some benefit in changing this policy. I'm going to call this sequence of distribution a policy. And one of the ideas that was given in this work by Nutini et al. Is the Gauss-Southwell rule, where it has been shown to be efficient to choose the coordinate having the largest gradient. So this IG is going to be important in our work. All right, and now if you look to other works where you have a noisy F and a noisy gradient, then you have this sparsification method literature. You have many other works inside. And in that, it's totally different because what they do can be compared to what I'm going to present. But there is a step that is different, that they really want to use unbiased gradient in the end. They use a reweighting strategy so that they have an unbiased gradient. We don't. What we promote is the use of biased gradients. So this can be seen in this slide where I introduce some notation. So in fact, if you look at our procedure, it can be written as a vector. And here you have this matrix D that is a diagonal matrix, and it's going to select the coordinate of interest. So you see, in that way, it's related to the condition gradient descent, where you have a conditioning step which multiply the gradient direction. All right. And here, what is important with this matrix D is that if you take its expectation, you recover a probability measure. And this is the policy that we wish to update. So now the problem is to run this algorithm and to know how to tune the D matrix. This D matrix. Those weights are going to give a different importance to the different coordinates. All right, and if you look at the mean field of this algorithm, you have typically something which is similar to condition gradient descent, because you don't recover exactly the gradient here. You have to multiply the gradient by some matrix. All right, so this is our goal, is to tune well this matrix D so that you have a nice procedure in the end. All right, so here is the full picture. If you take general update of that kind, which is what we are interested in, you can recover stochastic gradient descent if you choose H as G. You can recover condition version by using a matrix CT. You can recover the coordinate sampling that we do here. And now, so as I said, the sparsification literature about gradient descent considers, at least, from what, from the best of my knowledge, they always do this multiplication so that they multiply the D matrix by D minus 1, which is the expectation, so that in the end, if you compute the expectation of that, you recover the gradient. All right, so it's not exactly the same mean field. And in that aspect, I believe they kind of they have a loss in efficiency, because if you look at our simulation results, our experiments, the way it behaves is in the same way as stochastic gradient descent for most cases. All right, and we don't. We have a totally different regime. All right, so the algorithm that we design is called Musketeer. So each of those names correspond to something in the algorithm. But the main, our main interest in calling it Musketeer is for this motto of the novel by Alexandre Dumas. So if you know the picture, which might be of interest, is if you look at this problem to maximize over theta minus f, so this is the same problem as that we face. So we wish to optimize a function, and optimizing that function is climbing up that mountain. So we have 3 musketeers. Here is Athos. Here is Aramis, and here is Porthos. So each of those musketeers is a coordinate. All right. So we have 3 coordinates to get up that mountain, to climb up that mountain. And in the first place, what I'm going to do is one for all step. All right. Only one is going to move. So I'm going to choose at random, according to this D matrix, I'm going to select one of the musketeers. So let's say it's Athos. So Athos is moving, is going along its gradient. All right. So next, I can do this step many times. I'm going to choose another musketeer. So let's say Aramis. Aramis is moving. And then I'm going, after some stages, I'm going to stop that. And I'm going to move to the all-for-one phase. What they're going to do, they're going to share their gradients. All right. To move, they have collected some gradient value. And at this stage, they're going to share their respective gradient value. All right. This gradient value is going to be important because in the next stage, we can update this D using those gradients. And we are going to favor musketeers having large gradients. So if, for instance, Athos is saying, okay, my gradient has been 2.5. Then Aramis stage, you can see, okay, my gradient was a little bit less. So in the next stage, I'm going to trust more Athos because he has shown good gradients. All right. So the message, the idea is to follow the gradients. All right, to choose the musketeers. So if I write using some math, the 2 phases. So here is the one for all. In the one for all, you keep fix the D. Okay, the D is the distribution according to which you're going to sample, and then you're going to draw a zeta. Zeta is a coordinate. After that, you're going to move only the zeta coordinate for your algorithm. Okay, and you keep track. This is really important. You keep track of the gradient that has been used. So you update the value of this gradient. And this capital G is kind of an estimate of the gradient for that precise direction is going to be used for D. As you said, in the all-for-one phase where musketeers are going to share their knowledge, the D is going to be updated in that way. First, so let's look at the first part of the mixture. So the first part of this mixture is only saying that, okay, let's trust musketeers with large gradients, all right? And plus I have another part which is just for theoretical issue, so that I have a lower bound on this D coefficient. All right, so this part is, well, I don't like it that much because it's just for theory, and I'm not sure that in practice it's relevant. It still can be seen as a way to continue the visit according to all the coordinates. All right? Yes?
So when you implement this view, you implement it in both scale because it looks like it can have like many issues.
Yes, we did. Exactly. We did that in log scale. And in the end, what you can see, so in a bandit algorithm, in a bandit framework, you have several choices to be made. And each of those choices you can play on different machines. And each of those is going to give you a reward. But the reward in the classical framework of bandits is always distributed in the same way. Here, what we have is that we have, in visiting gradients, we obtain a reward at each stage, but the reward is going to change according to the value of the iterates. So, for instance, a direction which can be rewardful at the beginning can have small gradient in the end. All right, so you might need to change which musketeer you trust. So here is a very toy example, very nice, because I consider first a function with rotational invariance, for which Musketeer is not at all appropriate, because you cannot see any particular direction which could be favored compared to another. Okay. Musketeer is really appropriate when facing this kind of function, when you have one coordinate according to which you don't want to move. You don't want to spend any budget to move according to here the y-axis. And when we run Musketeer, so we compare here for the example Musketeer with two different algorithms, the full gradient algorithm, stochastic gradient descent, and another one where I'm choosing at random uniformly the coordinate. So it's a Musketeer version without policy learning. And here you can see that Musketeer, in fact, at the beginning, it has found the good coordinate, okay, to play with. And in the end, because it's reaching kind of a minimum, so the gradients are all small, is going to visit the other coordinates more. So it's one of the particular things of the algorithm, since you are looking at the gradient. As soon as you reach some kind of an area near the optimal point, gradients are small, and everything looks like uniform in the end. Okay, so it's ready for the beginning. Yes.
What is showing graphs? One is X and one is Y.
Oh, excuse me for that.
Can we compare it?
Sorry. Okay, so in this graph, here it's level curves of the function. So as soon as you are in the blue area, as soon as you are better. Okay, so at the beginning you are far away, and here you are at this value for the function, and you want to reach the minimum value, which is this way. And so what we can see is that Musketeer playing on one particular direction is moving much faster than the other. And in fact, our belief is that most of the problems in machine learning, when you have plenty of parameters, are like this. You have many coordinates, and you don't want to play with it.
It's actually perfect. I think I told you you're going to present the widening value. Yeah. Okay. Next talk is also going to have this landscape. But
Okay.
like the question about this, does this get deeper as you go along the valley, or does it stay the same depth? The below landscape.
Sorry, I don't
Like
understand.
if you go along the landscape, does it get deeper? Or...
No, not at all. It's yes, it's like this.
Right.
Yes, you don't get deeper.
Okay.
It's constant.
Okay, thanks.
All right, numerical experiments. Okay. This is due to a remark by Rifferi, and he said, and actually he was correct, that if you compute a full gradient, all right, no, let me start the other way around. If you compute one coordinate of a gradient, then you will have some computations that can be used to compute the other coordinates. So you cannot compare really full gradient, like it's like P operation more than only one coordinate. You can take advantage of some computation when you compute one partial derivative. It can be useful in many algorithms. It can be useful to compute the other coordinate. So it wasn't really appropriate to our algorithm, and so we frame this algorithm in the topic of zero-order optimization, which is particularly suited to a black box optimization. So you have a function f, and you don't know it at all. You don't know any formula for this function. What you can do is just you can call that function. So what remains to do, if we want to use this Musketeer algorithm, is to have an estimate of the gradients. So here is the first very natural estimate. It's just in each of the coordinates, you compute an estimate of the partial derivative. All right, so it represents p plus 1 called to the function. So it's a bit, it's a lot. So you can do different strategy. For instance, you have the Nesterov randomized smoothing, which is based on only 2 evaluations, and you need to draw random variable according to normal distribution, but it could be a uniform distribution on the sphere as well. Here is uniform sampling. It's just the same as that, but you pick at random 1 coordinate, and in Musketeer it's the same as that, but you have a new way to pick the coordinate. So in our initial definition of Musketeer, we just select at random the coordinate, but as you can see, it could be done by selecting at random on the sphere with some different direction other than just the coordinates. So here you can play on the geometry of the problem a little bit, perhaps, but we did not engage into that direction. Right? So what is interesting in this example is that we, so it's synthetic data. So we took that from another paper related to sparsification method. And you can see that the covariance structure is really particular. You have a decrease for the variance associated to each of the coordinates, so that when you generate data, when you generate regression or logistic regression, then each of the coordinates is not going to impact the same way the outcome. All right, so you have a very, well, each coordinate is different from the other. And the more you go with the index K, the less impact this coordinate has on the outcome, on the response. All right, so it's very well suited for a Musketeer algorithm, and you can see that here the first 3 algorithms are stochastic gradient descent, uniform sampling, and the Nesterov, and they all behave more or less the same. And Musketeer is showing a very good performance on that particular kind of data. Yes.
Did you try IS for instance, like the optimization algorithm which uses the conditional matrices? Because they also do something similar.
We did, and the results were more like the first one, and it did not achieve. I have printed in the paper. There is here. It's just a selection of the, but we did that for conditioning metrics like Adagrad and so on. And it was, even if it improves a little bit, that the other, well, the standard basic method, it did not has the same improvement as Musketeer. All right. Yes.
So this is the data model. What's the model for the regression coefficient?
That's a good question. I think it was like uniform, like a beta equal vector of ones, as far as I remember. I need to check that. Okay, so now what we did is we found data sets from a popular repository. Here it's digits. Well, you have a number on a sheet of papers, it's unwritten, and you need to recognize it. So it's a multi-class classification. What is appropriate here is to use neural networks with, I don't remember which architecture we use, but we tried several different architectures, of course. Here again, the Musketeer algorithm is showing a very completely different behavior from a standard approach that treats the coordinate in the same way. So here it really well advocates for treating the coordinates differently, etc. All right, and we did the same, but here it was in the initial version of the paper where we use the full gradient, not zero order gradient, but gradient, well, partial derivatives. And we play a little bit on this eta parameter. And so when eta tends to go, so if you don't remember, I can get back. This eta parameter is kind of, well, it's the importance that you give to the gradients. So if eta is really large, you're going to trust only the largest gradient. All right. If eta is really small, then this distribution is going to be uniform. So it makes sense to play with eta to see that as soon as eta is going to be small, you're going to be comparable to the standard stochastic gradient descent, and you can take advantage of eta when you take eta large.
A few minutes left.
Few minutes left. 2 or 3. Okay. Okay, so it's done for the numerical experiments. And now about the theory that we did. So it's not much, but what we did is we use this assumption in order to consider zero order gradient. All right, so this assumption means that our gradient is not biased. All right, you have to face some bias of order h. This is achieved as soon as the function is kind of Lipschitz, for instance, and so h control for the bias, and you can also recover first order gradient as soon as c is equal to 0. So based on that, we can use any approach like the one of Nesterov and Spokony with randomized smoothing, or also finite difference, and of course the Musketeer way we generate the gradient. All right, and we have an assumption about the noise. So here, let me just mention that some are considering uniformly bounded nodes. So here you have a bound sigma squared that is independent from theta. Here we have this growth term that allows the variance to be large as soon as f is large as well. All right, so it's less restrictive than the uniformly bounded variance condition, which is done in several papers. We need f to be L smooth, plus we need to have this lower bound. Here are some Robbins-Monroe condition on the sequence of interest. So here is my sequence of gains, and plus the h squared is going to be smaller, needs to be smaller than gamma. Not that you can take h equal to gamma, which gives you kind of a simplification in the algorithm. I'm going to show you that right now. So under this assumption, you have that the stochastic gradient descent converges to 0 in that way, where the gradient of the iterate goes to 0. And what we wanted to show is, given that, which is kind of natural and classical in the literature, we want to know what we need for the sampling policy. And what we need is one of those three things.
Just I think I need to interrupt
Okay.
to stay on time. Yeah.
All right. Sorry. So just to conclude with this choice of the sampling policy. So here, as I said, we need to be lower bounded. So perhaps the most interesting part in our framework is the last one. For general speaking, we just need a lower bound on the D coefficient, and then you can have the convergence. So, okay, so the proof is based on martingale tool. So it doesn't use continuous time approach, but rather we keep the discrete time feature of the algorithm. To extend those work, we can look at a particular regime that will select the coordinate, but now I'm out of time. So thank you very much.
So while I set up the next speaker, I guess if someone has one question, we could go ahead.
Is the update scheme for the distribution D, you also have lambda parameter that you didn't buy the structure. How does it appear here?